Alrighty. Um, so I, s- I was working on yesterday's challenge problem that had lapsed, and I couldn't make the deadline to keep my streak, but I did find a way to solve it, and I'm gonna go over the go over my thinking and how I worked it. So the previous approach I had, which was using a heap to determine like the possible next lowest product that you're going to look at and iterate over all the possible products. Uh, uh, I tossed that out after I realized it was just not fast enough. So that was going to be, what speed was that going to be? That was going to be, I want to say O of n times m, where n and m are the sizes of the arrays. So it's basically an O of n squared solution. Um, I was originally thinking that that might be good enough, uh, but maybe that would have been like 25 times 10 to the fourth. In case this is not good enough. Um, so the other approach I ended up using was a kind of a binary search. Yeah, it's a binary search approach. Um, and I'm gonna go over that here. So, and I'm sorry if I didn't stream it because I wasn't sure how long it'd take me to actually do it and whether any given stream would actually have anything useful. But for the binary search approach here, if you think about searching for a certain product, that product is going to be above some number of other products in terms of the order of the possible n times n different products that you can get, or n times n values you can get. Some of them are going to be repeated, but whatever. So for a given product, it's going to be above some number of other products and below some other number of other products. And you can search for it if it's too small, like if you're looking for k is 1,000 and the product that you guessed is above 500 different products, then you would guess a higher product. You would guess like, you know, instead of guessing 10, you might guess 50. Or if k is 1,000 and the product that you guessed was too big, like say the product you guessed had 5,000 products that were smaller than it, then you guess a smaller product, and then you keep on guessing until it's exactly right, or until it's right. The issue, well, that's the kind of the big overview, but uh, binary search generally works as long as you have a fast fast way of identifying whether or not a given search value is is okay or not. So if it is too big or too small, um, you can do that in like one pass of your data. So generally, the speed of the search, the speed of the check is going to be um, O of n, where n is the size of the data. In this case, O of n plus m, where n and m are the size of the arrays. So you have to do it in one pass. And if you can do it in one pass, and generally when you play hot cold, finding the correct value, that's going to be you know that's going to be O of log n or log base 2 of n, because you can eliminate half of the search space each time you um, each time you have a search value, right? So the question was like, can I come up with a single pass determination of how many products are smaller than how many possible products are smaller than a given product um, with those two arrays. So um, so first you just to help me kind of decompose the problem, create just a bunch of variables that would be useful. So finding the length of the arrays. I based on how I misspelled the nums1, nums2 with just num1, num2, I just really named it array1, array2, or AR1, AR2. So length1, length2 are the size of those arrays. I had a horrible way of doing this the previous time, but I was just going to split it up into the negatives and the positives because those are going to contribute differently for the products. It'd be a lot simpler if this problem was just all positives or non-negatives. But anyways, so split is where you would index for value 0. And this is to determine negative and positive subarrays. So using bisect left, which is finding the insertion point of a given value for this array. So where I would insert 0 into the array is where you would be able to split the array from things that are negative is things that are before this index, and things that are positive or non-negative would be things that are at this index and afterwards. So that's going to be where split 1, split 2 come into play for those arrays, and then I go ahead and split those two arrays, making -1 be the negative values for array 1, pos1 is positive values for array 1, using kind of split syntax, splicing syntax for Python. I wonder if I use splice correctly. Is this splicing? I think this is splicing. You can also say this is anyways, splicing is just getting a subarray or a certain subarray for between two indices. Alright, so get your negative and positives for each array, and then get the counts of the number of those, and then you get the count of the total number of negative products, where the negative products is either multiplying something that is negative in the first array with something positive in the second array, or something negative in the second array with something positive in the first array. So for example, like this one here, negatives would be -2, -1 from the first array, and then you can multiply it by 2, 4, 5 in the second array, so that'd be like 6 there. Or negatives would be -3, -1 multiplied by 0, 1, 2. Obviously, 0 is kind of included as a possible product because I didn't want to say non-negative a bunch of times instead of positive, but technically, yeah, technically it's non-negative. But you can get 0 as a product, but that'd be the highest product possible. And like here, the lowest product possible would be like -2 times 5, which is -10, or -3 times 2, which is -6. So smallest negative is going to be -10. In any case, this is going to help if k, anything that is, if you count the number of negatives that are produced in this fashion, and k is a number that is less than or equal to that kind of value, then that means that k comes from the production of it, because all these values are going to be smaller than the values that you get if you do a positive calculation or get a positive value. So like, obviously positives are going to be after negatives, and if you have, for instance, 2 times 3, which is 6, versus 2 times 3, which is 6, so you have 12 kind of negative values from that, 12 negative products from that calculation. And if k was like up to 12, then that means that you'd be searching in your negative space. Otherwise, you'd be searching in the positive space, where the positive space that are produced from multiplying 2 positives, like positives versus positives, or multiplying 2 negatives, negatives versus negatives. So anyways, just separating that out. So if your k value is in your negative product space, then to make the search a little faster, I don't think this is really necessary. This is just yeah, this setting the low and high bar to be something that is actually possible in your search space. So your lowest negative would be multiplying the value of the smallest negative, or the first negative in this case, with the biggest positive. So negative, the first value in -1 array versus the largest value in the +2 array, assuming that there are non-empty arrays. Similarly, you do that for the other one, smallest negative value in the second array versus the biggest positive value in the first array. That's going to be your lowest value, your most negative value, and your highest value is your biggest negative, which could be like -1 or -1 times your smallest positive value. So it'd be like -1 times 2 or -1 times 0. So technically high could be 0. That's why and when you set these initially, you want to do something reverse of that, since the logic of that's just how it works, right? And then this is simple binary search stuff, right? Or this is kind of not simple, but kind of template binary search. If this is your bounds for the product that you're searching for, and while the low is less than high, you find the midpoint to be your kind of guess search product value. Call on a sub function to helper function to search for the negatives, and then the results from that is going to be either 0, -1, or 1. If it's -1, that means it's too small. You want to get something bigger. If it's 1, it's too big. Then you get something smaller. Alright, so that's kind of the overview. And then my search function for searching negatives is this thing here. I have a count for the smaller values. I have a count for the number of values that are actually exactly equal to this product. The number of times this product occurs as the exact multiplication of 2 values from this first space. And then, so breaking it down further, you can either get, so you're searching for a certain product in let's say multiplying negatives from the first array with positives from the second array. So let's say my guess is like -6. So I want to figure out how many numbers that are smaller than -6, multiplying from here to here. So the smallest, so if I iterate over the indices of this one, so first index is going to be like index 0, it's going to be values -1, or sorry, values -2. I think if I'm guessing I guess -6. Well, let's just guess something kind of weird. Let's say I guess -5. So if I'm guessing -5, then I would do -5 divided by -2. So that would be 2.5. So um, so that means that I would need to have at least 2.5 as the positive value, the other value, because in order for it to multiply a negative with a positive to be smaller than -5, like -6 and smaller, um, it needs to round up. So the other value is the division rounded up. And then also I check the remainder to have some logic for when it's equal. I see where I find like -3 in the positive array, positive subarray using bisect left. And if 3 is not found, basically, like maybe all the values here are smaller than 3, so therefore the insertion index of this value, this other value, is at the end of the positive subarray, then I break this loop, because I know that this negative value cannot multiply by anything in order to be smaller than the product I'm looking for. So there's just 0 matches. And then secondly, because the loop is iterating over all the negatives, starting with the most negative to the most positive, the next iteration of the loop would not be able to find any matches as well. So like, for instance, if my product was, let's say, negative 500, and I find that -2 can't multiply by anything to get to a smaller value than -500, then -1 would not be able to multiply by anything to get to something smaller than -500, because it's like all the values -1 multiplied by would be even smaller than what I get if I, or more positive than what I would get if I multiply -2. So that's why I break this loop if I can't find anything. And then there's the check for the remainder being 0. So this is if this is the exact match. So if it's evenly divisible, this value negative into this product, if it's evenly divisible, and the value that I see in my search in the positive subarray matches the quotient, the division of how many times the value negative goes into the product, then this is exactly correct. And the number times it's correct, or the number of kind of pairings of this value negative with a positive value that is going to give me exactly the product, is going to increase by, so I basically search for where this other value doesn't stops. So, let's say that I'm searching for -6, this is -2, I'm searching for 3 as the other value. So where the index is first 3, which is index 2 is first 3, versus where index 4 occurs, or not index 4, the value 4 would occur if it was inserted in this array, then the difference between those indices would be the number times 3 appears, the correct perfect other, and that'd be the number times that I have an exactly equal product to the product I'm searching for. And then smaller is increased by the difference normally. So this is smaller than or equal to the number times I see a product that's smaller than or equal to the product I'm searching for. Do the same kind of logic for the reverse in terms of searching for negatives in the first, or going through the negatives in the second array, pairing it with the positives in the first array. Exact logic, pretty much. And then finally, if after all that I counted a smaller number of positives than k, like say I'm finding the 100th product, and there was only 50 products that were smaller based on this guess, then I'm going to return -1 because it's too small. I need to guess a smaller product, or actually I need to guess a bigger product. And then here's kind of a tricky one. If smaller includes the less than or equal to that value, so it could equal that value. So if I take away how many times it equals that value, and that is now less than k, then I turn 0. So this is kind of the perfect case. So kind of, let's say I'm looking for k is 5, and I find that there were 10 things smaller than the thing I guessed, but all 10 of them were equal to the value I'm looking for. So normally when there's 10 things smaller and when I'm guessing 5, I would think that maybe I guessed too big. But because all 10 things were actually equal to, then the 5th thing was actually part of the 10 things that were smaller than it. So smaller than equal to, all 10 were, so it's part of it. So if I kind of remove it, and now it's out of range, that means that within the range that removed was k. So I turn 0. And then otherwise, k is too big, and I need to get something smaller, so I return 1. So that was kind of the logic for searching the positives, or searching the negatives. And then for searching the positives, I mean, it's very similar. So I'll actually go back again. So there's this statement there. There's the binary search for the negative case, and here's the binary search for the positive case. So if it's a positive product, then the kth value there is going to be removed, or removing the number of negative products that I counted. So if I'm looking for the 50th product on the list, but there's like 20 products that are negative, then I'm going to search for the 30th positive product. So I'm going to move 50 minus 20, right? Or I'm going to move 20 from 50. Do the same process to find low and high. And so the positive product space is going to be multiplying negative times negative, or positive times positives. And the way that the logic of my code generally works, it's better if I use insert left, where insert left, or bisect left, where bisect left is where the first occurrence of it is. And just based on why that works, it's when I work through the positive combinations, positive times positive combinations, it's better if the positives I work with, as they are increasing, they have a reversed negative set that they're using as how they're calculating it with. So the logic is very similar to the other one, but I just had to make that change. In any case, so in just kind of going over this one less in depth, iterating over the negatives, and the reason is less obvious to me now, but I used going over the negatives in reverse fashion. So in general, I'm counting the smaller values than this product. So the smaller values are going to be based on a small negative number, like a -1, -2, -3, and then multiplying that with a multiplying with some negative value. multiplying with the other side of negative values. But anyways, it kind of makes sense to work backwards to start with the smaller negatives, like -1, -2, -3, and then go up. And if any time you can't actually find anything, then you break. Yeah. Again, because the negatives work in a fashion where you want to round up. Like if you have, let's say, the product is 10 and your negative value is -3, then the other negative value, in order for it to multiply to be smaller than 10, 10 divided by -3 is -3.3 approximately. You want to make that into a -3, right? Because if you make that into -4, which just happens when you truncate it, actually, I wonder if you actually need math.ceiling here. I'm pretty sure you do, but -3.3, if you do the ceiling of that, that becomes -3. And that is correct because your multiplication of -3 times -3 is +9, which is smaller than 10. If you're not, I think it truncates it to -3.3 to if you do product integer division with -3, I think it's -4. Actually, I'm not quite sure if this is necessary. I'm pretty sure I corrected something where this was necessary. In any case, this is fine, or this is correct. And then where that occurs, so like if I compare -3 or -2, -1 with -3, -3, -1, if I do -2 and I find that this thing pairs with, or let's say I do -2 and I pair it with this -3, then that means -3 and -1 would be fine to pair with -2 in order to get to something smaller than 10. Similarly, -1 would pair with -3 and -1 to something. So everything from the index on to from that index to the length of the negative subarray from array 2 is going to be smaller. And then lastly is the positive pairings, right? So the only real difference between this one is like the positives subarrays is where I stored my zeros. Positives were like non-negatives. So for the case where it's 0, everything's going to be smaller. Everything's going to count as a product that's smaller than the product, I guess. The product I'm guessing is at least 0 because it's a positive search. And if the product if in the very extreme case where I'm actually searching for the product being exactly equal to 0, then the things that pair with this value, which is the length of the other subarray, the positive subarray, is going to be equal. And then I skip over that value, otherwise I don't want to have something divide by 0 here. So here, divide by the value to get the other, and then the logic here is like, it's just the insertion logic or the bisect left logic. It's kind of convoluted, but I had to rearrange the positives, the second subarray of positive values to be negative, negative, so that it inserts, or it finds it correctly using bisect left. Otherwise, if you didn't do this, you just get some weird stuff, like you kind of either want like bisect right or you want to do bisect left and then do the index before that in order to do this count correctly. Anyways, I'm not going to try to fully explain it because I can't really even try to force my mind to do it. Anyways, find the other one, and then same deal, remainder. If the remainder is 0 and it matches perfectly, then increase the equal count. Same logic for smaller, smaller being something that you guess something smaller for, and then equal being exactly, and then otherwise return 1 if you guess too big. And then you have your binary search kind of template stuff here. While low is less than high, find your midpoint, do the search, change your low and high if the search is not perfect. Otherwise, turn whatever your mid guess was. Yeah. I was also considering as a wow, there's a lot of stuff. I was also considering as a possibility, because these two search things were very similar, making one kind of factored function from them, and then doing some sort of generic, like there's subarray 1, subarray 2, subarray 3, subarray 4, and then doing something based on that. It ended up being just too difficult to generalize to that extent, to kind of parameterize all this stuff into something even more general, because the logic was just too, I guess the logic was too difficult for me to kind of make that leap. And me having labels for the arrays that I'm dealing with, like negatives and positives, really was necessary for me to figure out what the hell is going on. Also, the fact that there's specific cases where things need to change up, like iterating over these in reverse fashion, dealing with the value that's 0, trying to in order to avoid not dividing by 0. Some of those cases only occurred in specifically to search positive or search negative, so couldn't generalize, although maybe a AI could. All right. So summary, I don't even know what to say here, but this is in general. It uses a binary search approach. And just quickly run to show the speed of it. Oh yeah, and I even bought a ticket to continue my streak. Alright, in general it uses a binary search approach, and here guess the correct product, and then or guess a product, count the number of products smaller than it in a sub. Am I using the word subfunction correctly? Subfunction, helper function. Subfunction versus helper function. Okay. I think they're both kind of synonymous. Count the number of products smaller than it in a subfunction. Here, the functions are search negative or search positive. And if that, and based on that count, determine if guess is too small, too big, or just right. So steps were kind of the big broad steps were creating subarrays for negatives and positive values, for array 1 and array 2. Determining if kth product falls under is a negative product or positive product, positive being non-negative, based on counts. And then creating a subfunction search negative to find if product is the kth in the negative product space, multiplying the negative 1s times the positive 2s, or the negative 2s times the positive 1s. Creating a subfunction search positive to find if product is the kth in the positive product space, and this is negative 1 times negative 2, or positive 1 times positive 2. And then here, this is, I guess the main thing that was difficult was actually this loop deal, right? So to count the number of smaller products, iterate over -1 subarray, determine find other, which is the product divided by the negative value, roughly, and increment count by number of values, number of positive values bigger than that. So, if the negative value is -5, the product that you're guessing is 60, then 60 divided by -5 is, or I guess this is the negative product space, so the product you're guessing is -60. -60 divided by -5 would be, well, let's say product that you're guessing is -60 value, the negative value is -5, then how many values in the other positive array that are above 12, right? -60 divided by -5 is positive 12. And you use indices, use bisect left to quickly find the quotient or the other value in positive array, and indices, particularly basically the length of the positive minus the index that you find, to use bisect left to quickly find the value in positive array and indices to determine count count of values. So if I find 12 as the 13th value and 20 positive values, then that means that 20 minus 13 is 7. There's 7 values that are positives that you can pair with this negative value to get a product that is smaller than negative 60. And then have some logic to count equals as well. To count number of times product exactly matches. Use remainders. And then lastly, return -1, 0, or 1, depending on the small count, the equal count, and k. So just those three things should be enough to figure out what this product that you're guessing is relative to the product that you're searching for. And then this thing is like very similar to previous, probably more difficult because the previous one was just negatives times positives. This one is particularly negative times negative or positive times positive, and that's kind of a more different case. But using negative times negative times negative, positive times positive. This is have special handling for zeros, since 0 is within the positive subarrays, positive arrays, and then have special handling for other stuff, or maybe insertions. Bisect left with positives. All right, and then I guess that's just 4 of the 5, and 5 would be use binary search general template along with search along with the subfunctions to return correct product, and a slight optimization is to use low and high product values from the actual subarrays, from actual values in subarrays. Normally, if you were to not optimize here, otherwise, your low would be like negative infinity, and your high would be low is negative infinity, high is like 0, or low is 0 and high is high is positive infinity, depending on when you're searching, depending on search positive or search negative or search positive. All right, time complexity, too long. No, it's going to be O of the search is O of log n to do binary search, and O of in general it's O of log n to do binary search. Okay, actually it's going to be O of log p to do binary search, where p is the size of search space or size of the product space, and O of n plus m to do subfunctions, the search positive or search negative. So overall it's going to be O of n plus m log p. Now p, the product space, is on the order of the product space, and the lengths are not necessarily the same, I want to say. I guess the lengths are on the order of 5 times 10 to the 4th, but the values themselves are 10 to the 5th to negative 10 to the 5th. I guess it's P. Okay, so, well, say if values in array 1 and array 2 have size of v, then p is equal to v squared. Yeah, because you're multiplying this some number in this thing times some number in this thing, so it could be possibly values in array 1, array 2 have size of v, maybe absolute value of v, where absolute value of v would be 10 to the 5th. The product space would be 10 to the 5th times 10 to the 5th. But you are doing log of it, so it's going to be pretty small. It's going to be trivial, kind of, compared to n plus m. Yeah, space complexity, this can be O of what did I do? Yeah, this O of n plus m, in order to create the subarrays for negatives and positives. Although it's possible, not needed, if you were to do strictly working through indices on the original array 1, array 2, it's possible that you could do that, because technically you are just, every time you're referencing -1, -2, you're referencing just indices, particular subsets of indices within the overall 0 to the length of array 1 or 0 to the length of array 2. So you didn't necessarily, I mean, it's just a lot easier to with the logic there. time to try today's